Hey students, as you guys are studying, getting ready for exam 2, I got this request. And so remember, this chapter is all about torque. Maybe just a quick reminder, if you go to turn something or pivot something, to make something pivot or to rotate, you need a torque, not a force. And remember that torque is more than force. So kind of a quick kind of review here is if maybe you had kind of a bolt and you put a wrench on it, and you grab the wrench maybe here, and let's just say we're going to go tighten the wrench, and so we push this way, so we've got a force, and it's going to then pivot the bolt around this point, and so this is the distance away, the perpendicular distance away, the lever arm. Keeping that in mind, that if I had pushed, maybe grabbing the wrench and pushed kind of in this direction, and then I kind of make what we call a line of action. Then again, from the pivot point to the line of action is the distance away. So you can see that the best direction, the most efficient direction of pushing something is perpendicular. So this blue one is the best way to do it compared to this red force. Because this red force, this perpendicular, which I'll label as R perpendicular for the red one, and over here I'll label this as R perpendicular for the blue one. Again, to get the most torque, you need a combination. In fact, maybe I should write the equation. So a torque is that perpendicular distance, that lever arm, times that force. So this is what I mean when I say that torque is more than force. That's why when we get to these harder problems, we need to stop and ask ourselves, are we looking at something that rotates or translates? Because if it rotates, the discussion is about torque. If it translates, the discussion is about forces. And so which are we trying to get? And as you can see, torque is more than just a force. So we are dealing in this chapter with things that rotate. You're being introduced to a more advanced topic of mechanics, a torque versus forces. And of course, to understand a torque, you got to understand force. And then you got to do a little bit of geometry to understand the perpendicular distance. And so you could probably see here that if I had two forces, one in blue and one in red, the blue one would give me more torque than the red one. And I'm going to assume that I'm pushing with the same amount of force. But because of the particular geometry, the angle at which you push it, the perpendicular distance right here is further than the red perpendicular distance, as I kind of show here in the diagram here. So that's what we got to keep track of when we do torque, not just the force, but also the appropriate direction to then get the perpendicular distance. All right, so that's kind of a little mini lecture, if you will. Let's actually do this problem here. So we got two children. One has a mass of 20 and the other has a mass of 30. And they sit balanced on a seesaw with a pivot located in the center of the seesaw. So drawing a physical picture of that, I might have maybe this pivot here, and then I've got this seesaw that extends out. Okay. And maybe I'll just, they put it right in the center with the idea that it would balance on its own because this half and this half are, symmetric, and that alone makes them balance. But clearly then if you put a child on here, and so let's do the child that has 20. So we'll just make a little blob here and say, okay, here is 20 kilograms. So the force of gravity then would technically be the mass times g. And then there is some perpendicular distance away, which I'll draw in blue. Because the other child sitting on the other side weighs more. They're 30 kilograms, so their force pushing down has to be 30 g. And then, of course, they would have a perpendicular distance. But a very key word in this problem, where is it? The two children are balanced. There we go. And the word I'm looking for here is balance, because what that would tell me then is this blue over here with the lighter child is making a torque that's going to rotate it. Let's see, from your viewpoint would be a counterclockwise rotation. And then the same thing is happening with the heavier child in the red over here, although it's making it rotate in a clockwise direction. And so we have competing torques. And like competing forces, you know, equal and opposite, there's no net movement. That's what I have here. There's no net rotation. And so what we're saying here is that this force, 20 times G times R perpendicular in the blue, and maybe just to put a number so I can keep track of it, 1, is then equal to this force, 30 times G times R perpendicular, and we call it number 2. And so those two torques are equal. They are balanced. Had they said that it rotated, you know, towards, or the 20 kilogram child went down, then I would say this torque is greater than that one. Or if they put it the other way around and it rotated this way towards the heavier child, I would say the torque then, or this torque is greater than that torque. And again, notice that it doesn't necessarily rotate in the direction of the heavier child, because this lighter child can move out, giving it more torque than what is gotten from the heavier child. So it's not just about force, it's about the amount of torque, which includes lever arm. So it's not always just going to rotate in the direction of the heavier child. It depends where they sit. Now, I knew that the distance of the red one is going to have to be a little bit lower because the force is greater for those to be equal. So I hope you can see that in my drawing, that I deliberately drew a longer distance for the lighter weight child than the other way around, so that these torques would be equal. Okay? Now, let's keep working on the math here. It says, if the children are then separated by 3 meters. Okay, so that statement is saying that R perpendicular 1, and I don't know if I'm going to keep up with the color code here, R perpendicular 2 equals 3 meters. Okay, and now we have a system of equations. 2 equations, 2 unknowns. And so we can solve for both R1 and R2. And I think that's going to be the question here. Let's see, if the children are separated by 30 meters. At what distance from the pivot point is the smaller child sitting in order to attain balance? Well, let's do both of them, but they say the smaller child, so they're looking for what I've called number 1. So let's find number 1, but let's also find number 2. All right, so let's just kind of rewrite these equations, and I'm kind of limited with my paper options here. So I don't have my normal setup here. So let me go ahead and just write those 2 equations. So the first equation was a 20GR1 equals then a 30GR2, if I'm not mistaken. Okay. And then R1 and R2, so R1 plus R2 equals 3. All right. So again, 2 equations, 2 unknowns. And just to make things a little bit easier, why don't I take that first equation and divide both sides by G? And that's actually kind of nice. And actually, I wouldn't surprise me if some people started this problem and they just totally forgot about the G. Remember, force is both mass and the 9.8 mg. But you can see in this case, if you forgot about it, we're still talking the same thing because both children are being affected by G the same way. So I'm not even going to bother to mess with the 9.8 for G. What I am going to do, though, is take this first equation and bring the 20, or divide both sides by 20, so I'll get an R1 equals to 1.5 R2. And then I will use that and substitute it into the second equation. So R1 becomes 1.5 R2. And then, of course, plus R2 is 3. So we add those together, and it is 2.5 R2 is equal to 3, or R2, and that's not the one we want, but like I said, I'll do both. So we get 3 divided by 2.5, and so the heavier child is right here, 1.2 meters away from the pivot. Now, of course, we can use that back up to any of these equations. I'll just use that one right there. So this would say R1 is 3 minus R2. So that's 3 minus 1.1, which gives me 1.8 meters. Okay, and then, so there we go, 1.8 meters. And that's what they were after. How far does the lighter child? 1.8, and the heavier one, they didn't ask, but we're there anyways. And so that's kind of the theory. Well, I guess this is the theory of the torques. This is applying the torques, and then now here's working out the math, 2 equations, 2 unknowns. Hope that helps. Bye now.